Hello, am I audible? Hello, can you guys hear me? Hello, am I audible to you?
You're audible.
Okay, so hello everyone. So this week we will be solving problems from trusses. So to solve the problem in trusses, we will be using method of joints and method of section. And before going to that, we still have one left problem from the equilibrium of forces and movements. So this is for from the previous week. So the one problem I gave you for just to practice, and this is another last problem of it. And then we will move to truss. And then after this lecture, I will upload this and the truss PDF simultaneously in the Google Drive. So this problem is a bit related what we are going to do today in the entire class. And in this problem, there's a crane arm has a pin support at A. The hydraulic cylinder BC exert a force on arm at C in the direction parallel to BC. The crane's arm has a mass of 200 kg and its weight can be assumed to act up 0.2 meter right of A. So somewhere here its weight is acting, or I should draw here, which is 200 multiplied by 9.81 Newton. Okay, and it's 2 meters. Sorry, it's 2 meter uh, from point A here. If the mass of the suspended box is 800 kilogram, so here the weight of this box is 800 multiplied by 9.81 Newton. And the system is in equilibrium. What is the magnitude of the force exerted by the hydraulic cylinder? So basically we need to find the force in this, and we will be using the equilibrium principle because in the question it is given that the system is in equilibrium. So we know what to do. So first let's make a schematic diagram or the force free body diagram. So if, let's say this is my point A, which is pin jointed, so there will be two reaction. This is AX and this is AY, and this is the arm, and there is a weight here and here. Then there is a force which is acting somewhere here, which is BC. Okay, so this is our rough free body diagram, and we need to find the force in BC. So we know the what are the unknown forces here. We have 200 multiplied by 9.81. We have 800 multiplied by 9.81. We have the unknown force uh, on on this hydraulic cylinder, and we have unknown reaction AX and AY. So first let's find out the angle theta. So we will be finding this angle theta. So we know this distance and we know this distance. So we can use 10, we can use the formula of tan theta, which will be 1.2 divided by 2.4. So it will be theta equals tan inverse, sorry, it will be other way around, 2.4 divided by 1.2. So it will be 2.4 divided by 1.2. So if you solve this, you will get tan equals 63.4 degree. So this is our theta. And then we will be using equilibrium equations. So first, the summation of force in the fx direction will be 0, and there is ax, and then there will be a component of this force, component of the force which is acting in the x direction, which is fh cos 63.4 equals 0. So this is equation 1. Then we do the summation of forces in the y direction. And here we have ay and two weights. So it will be, and also the vertical component of this force, this. So here will be ay fh sine 63.4 minus 209.81 minus 800 multiplied by 9.81 equals to 0. So from these two equations you can see that we can actually find, so there are three unknown, ax, ay and fh. So we need third equation. So the third equation will be the moment balance. The summation of moment should be 0. And if I take the moment at point A, then actually I can find the force Fh, because there is a movement from this force, component of this force Fh. So there will be a movement due to these weights. So this weight has a perpendicular distance, you can see here. It's 7 meter and it is 2 meter. And this force component, hello?
FH, where is it? Where FH is acting?
Fh is acting under this red color
FH.
in this bar. Yeah, it's a oh, sorry. Let me write some another convention. I can write BC.
Oh, okay.
Okay. So
Okay.
yeah. Then for the horizontal case, this is my horizontal force and this is my vertical component, right? And it will be for the horizontal force, the perpendicular distance is this, and for the vertical force, this is my perpendicular distance for uh, force BC. So this will be, so this is my perpendicular distance for BC cos theta, and this is my perpendicular distance for BC sin theta.
For BC 1.2 only, right? 1.8 also you rounded up.
No, the force is acting here, right? So as this crane is moving downward, the force is acting here at this point at C. So
Okay.
this is the direction of force, and you have horizontal as well as vertical component. So for the vertical component, this will be your perpendicular distance, which is 1.8 plus 1.2. And for the For this horizontal component, the distance will be this, which is 2.4 minus 1 meter.
Okay, okay.
So in the moment equation will be,
The particle moment at A. Okay, right, sir.
yeah, yeah, at this point. So it will be FH sine 63.4 multiplied by 3 and FH cos 63.4 multiplied by 1.4, and due to weights, so this weight creating has a perpendicular distance 7 meters, and there is one more here, 200 multiplied by 9.81, which is 2 meter from point A, which is given in the question. So we have minus 200 9.81 multiplied by 2 minus 800 9.81 multiplied by 2 equals 0. And this is the third equation. So we can solve equations one by one. So the first equation will give AX equals minus BC multiply 0.447, and the second equation will give AY plus 0.894 BC minus 1962 minus 7848 equal to 0. So it will be AY plus 0.894 BC equals 9810. So this is from second equation and this is from first equation. Oh sorry, here I shall write BC. So from the third equation we actually get BC, force in the BC, so it will be two point 682 BC minus 0.626 minus 3924 plus 15696. So it will be equal to 19620. And this is 2.06 BC. So my BC will be 9.542 kilonewton. And if I substitute in equation 1 and 2, I can directly get AX. So it will be 4.19 kilonewton, and here so this will be 1.27 kilonewton. So in the end, we don't need to find these reaction forces because in the question we have asked to find the force in the cylinder, but nevertheless we first find the force in the cylinder BC and then the reaction AY and AX by using the equilibrium equations. So you can see that in all the question we have used the similar equations, so there is no very non-trivial concept that you need to learn here. The only little tricky part can be that the algebra can be messy, or maybe you need to find the angles in a very non-trivial way first, and then you can use the equilibrium equations. But anyway, the problem we saw in the previous class and in this one, we can see that we use the equilibrium equation in all the problems. And for the moment, to write down the moment equation, when you write the summation of moment equal to 0, you need to choose the point such that you will simplify the expression. For example, in this problem we choose the moment from point A. We could have choose from point C or like at the last point here. So it is very random. You can choose the point to take movement. You can choose any point, but you should be aware that the algebra should be very simplified, because if we choose the movement from point A here you can see that we can by using the only moment equation we can able to find the force in the cylinder. We don't need to use the force equilibrium equation separately. So these are the few things that you need to keep in mind. Otherwise the concept is very it's not very difficult. You just need to first see in the question whether the system, or analyze the question that whether the system is in equilibrium or not. Once it is, then you can use the summation of forces and the summation of moment to be equal to 0, which are the necessary condition to remain the system in the equilibrium. So in the first question in the first lecture tutorial we actually saw that how to calculate the total or overall force and movements. Then the second one we solve that we show that if the system is in equilibrium, these total force and the total movement or the summation of movement should be equal to 0. And now we shall begin with third topic, which is trusses. So in trusses we will be using method of joint and method of section. So in method of joints, what happens, we actually consider each joint of the truss individually, and then we use the force balance and moment balance analysis on that joint, and we keep doing until we find forces on all the members of the trusses. So basically the primary ingredient in this method is to use force equilibrium equations. So suppose we have a truss. So this is our truss, and here let's say we have a pin joint, and here we have a roller joint, and there are some forces which are acting here. Let's say this is A, B and C. So what happens? There will be a number of joints here. So we will be choosing each of this red joint, which is shown in this red color. Let's say we choose joint A, and then we will make the free body diagram A, C, B, and then using this free body diagram at joint A we will be using the using the equilibrium equation to calculate the unknown forces. So here this reaction, let's say this reaction RA, let's say it's a known forces, and we need to calculate unknown forces AB and AC. So in the method of joints you can see that these forces are co-current in nature, right? This force AB and AC are co-current in nature because their line of action is meeting at a single point, which is this point. So for this kind of forces, you need to use the equilibrium force method, or the equilibrium force equation. So here you need to use this equation where you take the summation of forces in the x and y direction and equate it to 0 because the system is in equilibrium. And then you keep considering all the joints here in this problem and calculate and using this same equation to calculate the force in the unknown members. Whereas in method of section, what we do that we actually put some random cut and we divide the truss into two parts. And this cut can be anything. You can cut like this, you can cut like a straight line or some inclined line, anything. And you can then see where this cut is actually passes from. So this cut is passes from member CD and BE. So your free body diagram will be this is your free body diagram. Now you can see that these two are the unknown forces, CD and BE. These are the unknown forces, and they are not co-current to each other. Unlike in the method of joint here, force AB and AC are co-current to each other, and therefore you just need to use the force equilibrium equation to find out the forces here. But here these unknown forces are not co-current in nature, and therefore you need additional equation that the summation of movement at some point, random point, should be equal to 0. So then in the method of section you will be mostly using combination of these equations to find out the unknown force in the unknown members. So the procedure is more or less similar to what we have actually looked into the previous class. We will be using the same set of equations, but we will be using two different methods. In the first method, we keep choosing different joints to find the unknown forces, and in the second method, which is a little easier, or I should say a little less time consuming, we actually cut the truss into two, divide the truss into two or three parts, and then use a combination of these two equations to find the unknown forces. Here you don't need to consider each joint separately because you already divided the truss into two parts here, and then you do the force and moment balance analysis. Okay, so you can use the method of section multiple times. You can again cut the truss, cut this truss into more number of part, or you can even use these two method in the same problem. So there is we don't have any such restriction here. So you can actually use the method of joint separately or method of section separately in the problem, or you can use the combination of these two methods. So it's all based on the inspection, I should say, because when you have a problem, you just inspect which method which method you need to follow. If you have given a very complicated truss, very large and complicated truss, it is always advisable to use the method of section, because in a large truss it is very inappropriate to go joint by joint because there will be many number of joints. So you can use the method of section in a very large trusses, but in a very small trusses, when you have a small number of very less number of joints or very less number of members, you can always use the method of joints, because people usually familiar by this equilibrium force equation more, and they find it convenient to use this force balance analysis at each joint. So before solving the problem using these two methods, we need to check whether the system or the trusses is in indeterminate state or not. So to do that, we have the equation m plus r equal to 2j. So here m is the member, here r is the reaction, and j is the joint. So if any truss satisfies this equation, that means the truss, you can use these two equilibrium relation to find out the forces and movements in the truss. So for example, Let's begin with a very simple problem here. Let's say we have a truss. Here we have a pin joint, and here we have a roller joint. So this is our truss. This is A, B, C, and D, and there is a force which is acting at point D, which is 2 kilonewton. And let the distance is 5 meter, and here it is 5. And we know that in a pin joint support we have a two reaction, AY and AX, and whereas in a roller joint we have only one normal reaction. So this roller, we can see in the figure that it can move freely in the vertical direction but not in a horizontal direction, so there will be only one reaction. So before solving any problem by method of joint and method of section, first always whether you can solve this problem or whether the truss is indeterminate or not. So you have to use this equation, and if it satisfies this equation, only then you can use the equilibrium or any method of joint or method of section to solve the problem. So here we have M is the member, and you can see that we have 5 members. We have total 3 reactions, AX, AY and BX, and we have total 4 number of joints. So you can see M plus R equals to 8 and 2J equal to 8. So it satisfies M plus R equal to 2J. So it satisfies this equation. That means we can go ahead and solve this truss by using method of joints or method of section. So first let's use the method of joint. So we will be using the method of joint in some 2 or 3 problems, and then we will move ahead with the method of section. So first let's consider an angle alpha here, and we need to find this angle because this will help us to find the component of the force like BC, AC. So angle alpha can be found out by tan alpha 6 by 10. So it will be alpha tan inverse 6 by 10. So alpha will be 31 degree. So this is my alpha. So now let's find the reactions. So to find the reaction, we will be using simply force balance analysis that we have used until now. So summation of forces in the x direction will be 0. So it will be AX plus BX. Equal to 0, and then we do the summation of force in the y direction, and we will have AY and 2 kilonewton here and 2 kilonewton here. So it will be AY equal to 4 kilonewton. Then the unknown is Bx and Ax. So we need one more equation, and we will be using moment equation at point A. So the summation of moment equal to 0 at point A, and the force which causing this movement will be Bx, because it has a perpendicular distance 6 meter. It is 2 kilonewton. It has a perpendicular distance of 5 meter, and this force which has a perpendicular distance of 10 meter. So here we have, and I am considering clockwise movement as positive and counterclockwise movement as negative. So Bx will rotate in a counterclockwise direction about point A. So it's a negative. This 2 kilonewton will rotate in a clockwise direction, and this kilonewton also rotate in a clockwise direction about point A. So we have 2 multiplied by 10 plus 2 multiplied by 5 minus 6 b equals 0. So it is 20 plus 10 equals 6b. So b will be 30 by 6 or 5 kilonewton. So this is our Bx, which is 5 kilonewton, and by using this equation you know that Ax will be minus 5 kilonewton. So the direction of Ay, which we assumed this, it should be this 5 kilonewton or this minus 5 kilonewton. So in the left direction it is 5 kilonewton, and in the right direction it is minus 5 kilonewton, and we will talk about this more, that how to identify the direction in the truss, or how to identify whether the member is in compression or is in tension. So we now know the reaction forces. So let's consider joint A and calculate the force in this member as well as in this member. So first let us make the free body diagram of joint A. So this is Ax, this is Ay, these are my axes, x and y axis. This is force AB. So I'm just guessing the direction for now, that the direction of force AB is in the downward vertical direction. You can also choose to be in an upward vertical direction. I'm guessing in the downward direction. And this is force AC, and this is alpha, right? So again, for the force AC, I am guessing the direction to be in downward in the y, or in the negative y direction, and positive x direction. So as I said, for at each joint you need to do the force balance analysis, because these forces are concurrent in nature, and therefore by using the force balance analysis you should get the unknown forces, assuming that the unknown forces is not more than 2, because otherwise you will also need the moment equation. So the summation of force in the x direction is 0, and we can write minus Ax, because this is in minus x direction, and plus FAC cos alpha we found 31 equal to 0. So minus Ax was 5, so just observe here, we already changed the direction of Ax, because earlier in the question we assumed that the direction of Ax is on the right hand side from left to right, and we found that AX is minus 5 kilonewton. So we change the direction of AX. So I don't need to consider minus 5 here. Okay, so just observe this. So here we have minus 5 plus 0.85 FAC equals 0. So we will have minus 5 equal minus 0.85 FAC. So FEC will be 5.88 kilonewton. So you get the positive 5.88 kilonewton. So which means that you don't need to change the direction of force AC. So your assumed direction is right. So you assume direction here. I'm already showed the assumed direction of force AC, and I found that it is positive. I got the positive 5.88, which means my assumed direction is right. If it would have minus 5.88, then I need to change the direction of this force in the opposite direction. But our assumed direction is correct here, and to determine whether the force in the member is having a nature of compression or detention, you should always have one convention. Suppose this is your joint, and if the force is away from this joint, then it's a tension. And if the force is towards the joint, then it will be a compressive force. Okay, so here you can see that the direction of force is away from the joint, which means this is a tension. This is a tension force in the member. Okay, so just don't go by with the sign. Suppose you got 5.88 and you can just blindly tell this is a compressive force. It's not a correct way. Just see the free body diagram. If it is minus 5.88, the force is towards the joint and it would be compressive. But this is not true in all the problems. So just see whether just actually compare the direction of force with respect to the joint, and don't say whether it is a compressive or the tension just based on the sign here. So we can see that it is going away from the joint, which means it's a tension force. Then now we can find another unknown force, which is force AB. So now we do the force balance analysis in the y direction, and we will have AY minus force AB. Our assumed direction is in minus y axis, so this is minus y, this is minus x, and there will be a component of force as well, which is minus FAC sine alpha. So we know AY is 4 kilonewton, and force AC is 5.88 sine 31 equal to 0. So it will be 4 minus 3.028 equals force AB. So force at AB will be 0.9 7 kilonewton. So So this is our force. So again it is a positive force, which means the assumed direction here it is correct, which means the force AB actually, the direction of force AB is along the minus y axis, and you can see that it is going away from the joint, which means this force also is tensile. So this is how actually you calculate the forces by using the method of joint. So you first need to determine whether you can able to solve by these two method, and whether the trace is indeterminate or not. It is static indeterminate or not. So for that you have to check by this equation. Once this equation gets satisfied, then you can use the method of joint or method of section. So by using the method of joint, we use, since we know that all the forces at one joint will be coplanar, and therefore, and if the unknown forces is 2, we can only use the force balance equation. And using this force balance equation, we actually can find the magnitude of the force in each members. Now whether to check if the force is tensile or compressive, we need to use a simple method that you can check from this joint. If the force is going away from the joint, then it's a tension, and if the force is going towards the joint, then it's a compressive force. So by using this method, you can actually verify that, or you can actually say that if the force is tensile or compressive. So any doubt till now? Okay, so we can solve one more problem from the method of joint. So this problem is also not very complicated problem. It's a very easy algebra, and all we need to use is the force balance equation. So in this question, we need to determine the axial force in the member of truss and indicate whether they are in tension or compression. So let's start with the joint A. So first let's check whether this truss is static indeterminate or not. So we will be using m plus r equals 2j. So the number of members are 3 and the number of reactions are 3. You can see this is your pin joint and this is your roller joint. So here you have only one reaction, but here you have two reactions. So your total number of reaction is 3.
Himanshu, I have a doubt.
Yeah.
If any special cases, that means if B and C have joints, which means pin support and the roller support. In between, perpendicular to A, another one pin joint is coming, means another one support. And A to the perpendicular joint, one what is it? One truss is connected, means that time what is the reactions?
So no, so this is for any pin joint. So pin joint, every pin joint will have two reaction forces, because see, for the roller cases you have only one reaction forces, because this roller joint you can actually move in the horizontal direction, which means there will be no reaction force in the horizontal direction. But this roller joint is actually make this, it actually constrain the motion in the vertical direction. So this is not possible. The vertical motion is not possible because the vertical motion is constrained. So there will be a reaction force, vertical reaction force here. But pin joint, what pin joint does, it actually constrain both horizontal and vertical motion. And that's why you will have the reaction in both the direction, Rx and Ry. These reaction forces are there because it is constant both x and y direction motion. Whereas in the roller joint, it constant only y direction motion, and only that's why only you will have reaction force in the y direction. But it can actually move in the horizontal direction. That's why you have a rollers here. So it's not constant in the x direction, and that's why you cannot have the reaction in the x direction. So if you replace this roller joint with a pin joint, then you will have a four reaction. You will have two reaction here, and you will have two reactions here.
I'm asking if you add another one support, if I
If
adding me.
if you have another one support, for example, here you have
Yeah.
pin joint, then you will have again this and this two reactions here from this pin joint, because this pin is experiencing forces, reaction forces in both the direction rx and ry.
Mm. Okay.
Yeah.
But what I thought is
So it's like, I mean, so you can also think like this. So for example, you have here pin joint, you have here a roller joint, and this is a one member continuous beam. But let's say you have here pin joint, then you can actually consider this member as equivalent to member, like this, with one vertical reaction force, like this, because these are also pin joints, right? These truss are connected to each other by various pins, like in above in above diagrams, these trusses are actually connected with some kind of pin.
mm.
But here you will have extra vertical component of force as well.
That time my R will increase, right? M plus R do J is there, right?
Yeah,
That
yeah,
time.
yeah, yeah. So then when you when you actually add extra pin joint, the system will become redundancy, which means that you will have more unknown. So for example, here you have unknown ry, r2y, and let's say r2x, and here you have R3y. So now you have four unknown quantities. So for four unknown quantities, you need four equations, but you can only use three equation. You already have three equations, and you at most you can find three unknown quantities. So it's like you have more unknown quantities. So the system will become redundancy, because you don't need to add a pin joint here to support the truss, but you are adding the pin joint, plus you are actually bringing more unknown number of forces, and that happens when this relation m plus r is more than equal to 2j. So when this condition happens, then the system is redundancy in nature, which means you have a more unknown number of forces than you can solve for.
Understood.
Yeah. So let's consider so here we have m equals 3, r equals 3, and j is 3. So you can see that it is satisfying this equation, because it will be 3 plus 3 equals 2 multiply 3, which is 6, which is balancing the LHS and RHS. So this truss basically satisfy this equation, so you can easily use the equilibrium equations to calculate the force uh, in each member of the truss. So let's make a free body diagram for the whole truss. This is A, this is B, C, let's say this is BY, this is BC, sorry, this is CY, this is BX, and it is a force which is acting 800 Newton. This is zero point 0.4, this is 0.7 meter, this is 0.7 meter. Okay, so now first consider joint A. So this is my joint A, and also it is very advisable to define your Cartesian coordinate system. So here it is x and y, and this is the force 800 Newton. Okay, so now this is force BA, and here it is AC. Okay, so now we can use the force balance equation at this joint. So it will be force summation of force in the x direction equal to 0. So it will be minus 800 sine 20, and then there will be a component of BA and AC as well. So minus, so this is the component of force BA, so I can use these sides like 0.7 and 0.4 to calculate the components, and we have discussed this in first lecture, that how to use the sides or angle to find the component. So it will be, so if this is 4, this is 7, then this will be 65, root 65, and here the force AB is acting, force AB is acting here, and we need this component of force, right? So it will be 7 by 65. Now this force, horizontal component of force AC, is in the positive x axis. Okay, so if we are going to use sides, and this is our force AC. Okay, so if you want to calculate the horizontal component, this component of force AC, then it will be 7 by root 65. If you want to calculate vertical component, this one, then it will be 4 by root 65. Basically I am just using sine and cosine. This is 7 by root 65 is just cos theta, and 4 by root 65 is just sine theta. So to calculate the horizontal AC, it will be 7 by root 65. It is equivalent to sine theta. That's, sorry, cos theta. That's it. And equal to 0. So this is my equation 1. Then we do the force balance in the vertical direction, which is equal to 0, and we will have minus 800 cos 20, and we can see that all the forces is in the minus y axis, so all the forces are negative. So here it is BA 4 by root 65 and AC 7 by root 65, sorry, 4 by root 65 equal to 0. So there are two unknowns, AB and AC, and two equations, so we don't need another equation to calculate the unknown force in this joint. So we can simplify equation 2. So this is from equation 2. I can write AC as minus 751.75 minus 496 PA. So my AC will be 1602.878 minus BA. So I can put this force AC in equation 1. So from equation 1 I am having minus 273.6, which is basically 800 multiplied sine 20, minus 0.868 BA plus 0.868, and then instead of AC I will put this expression here, minus 1602.878 minus BA equal to 0. So we have one unknown BA. So it will be minus 1390.53 minus 0.868 BA equal to 0. It is 1664.136 minus equal to 1.736 BA. Solving this, we will get BA as some 970 Newton in negative. So we are getting minus 970 Newton in negative, which means the assumed direction of BA is not correct. So we assumed in a negative y direction, negative x and negative y direction, but it should be in this direction. Okay, and you can see this, the correct direction is shown by black arrow, and it is going towards the joint, which means that the force is compressive. So this is compressive force C, and we can actually find force AC as well from this equation. So it come out to be minus 632 Newton. So again, our assumed direction of AC again it is not correct. So it is this direction. This is the correct direction, and we can see that the correct direction is going towards the joint, which means force AC is again compressive nature. It has a compressive nature. So these are the force AB and AC. Now we can actually calculate the force, this BC, force BC, this one. So let's consider joint C. So let me write what we actually found. So AB is 970 compressive. and AC is 632 compressive. So here you don't need to bother minus and positive sign, because whenever you make the free body diagram, since it's a compressive force, this AB will always be towards the joint, and same goes with AC. So whenever you make any free body diagram in other joint, let's say you at joint C, just denote AB or AC, whatever the forces will come in that picture, towards the joint, because both are these compressive in nature. So let's consider joint C. So here you have CY, and let's say this is our BC. I'm assuming in the negative X direction, and your AC is towards the joint. This is our AC. So you can see by inspection that if you do the force balance analysis in the X direction, you will have equal to 0, then it will be BC, negative BC plus AC, which is 7 by 65, equal to 0. Then you have minus BC. AC was 632, so 632 multiply 7 by root 65 equal to 0. So minus BC equals minus 632, and 7 by root 65 will be equal to something 0.86. So BC will be positive. So the assumed direction is correct. Because it is positive and the magnitude is 548.88 Newton. So this is the force BC. So we don't need, so we actually already calculated the force in all the members. So just to recap here, we need to use the method of, we use the method of joints to calculate the force in all the members. So first we see that we can actually check whether the system is in static indeterminate or not by using this equation, and it satisfies this equation, which means we can proceed by solving method of joints. And then we consider joint A, and we use the force balance analysis to calculate the joint in this and this members. And then we analyze how to say whether the joint is in tensile or in a compressive force. And we found that we got the negative forces, which means our assumed direction was wrong, and um, we need to correct the direction there. Then we actually consider joint C and calculate the force in this bar as well and assign its direction. So you can see that it's a positive 548. That means the assumed direction of BC is correct, and it is going away from the joint, which means this tensile. So the force in this is compressive, and the force in this joint is tensile in nature. Okay, so any doubt until now? Yes.
Uh, See, I have the doubt which I asked you last week.
Yes, yes.
And did you get any answer? Did you get any answer for that?
Yeah, yeah. So, yeah. So I mean, for that, let's consider a system. So I was looking for the system. Let's say this is point P,
Mm.
and there is it exists in some line. This is line L, and let's say I want to find the moment at this point P,
Yeah.
and the moment is this. So first, let me draw the displacement vector, which is, let's say this is my displacement vector, and this is my direction. Sorry, force vector. And you can see that the direction of movement will be perpendicular to this, and it will be somewhere here, MP, and the movement
Okay.
will be r cross f. Now I want to calculate, so this is my direction of movement. Now I want to calculate the movement, let's say along this axis. Wait a second. So this is my movement MP here, and now I want to calculate the movement along this axis. And let's say this axis I can represent it by a basis vector E. So what I will do that I need to take the component of this vector MP along this direction. So the direction of this vector here, I need the projection of this vector MP along this direction. So I can write this as ML equal to projection of projection of this vector along this axis, along the axis which is defined by E vector. So this will be my projection, and this will be my movement along this E vector ML, and I can write ML as
Uh, uh,
E dot
it should
uh,
be only E dot MP.
yeah, this will give you the magnitude, right? But since this is a vector, you need you you need a vector quantity at the right hand side also. So E dot M will give you the magnitude of that vector, because these are the vector, so it will give you
Okay.
some scalar, right? This is a scalar quantity. It will giving you the magnitude of that projection vector of the vector ML, of the vector here, ML vector.
Okay. Yeah, yeah, yeah. Yes, yes.
So this will be
Mm.
your the movement at different direction, which is you can calculate by projection. You can also do the projection vector here and like here. So basically you are finding the component of vector MP, and that you can do by projection.
Yeah.
Yeah. So this is your whole vector, and this
No,
in
but
Hmm.
yeah, please go on.
So I'm just saying this is your whole vector, and the quantity inside the square bracket is the magnitude of that vector.
Mm. But in slide it was written E dot R cross F. Not bracket is not there in R cross F. So that's why I told you that E dot R gives a scalar and it will not cannot be multiplied by vector F. Like
Yeah.
in that slide, this here I understood what you are making point. Like here you have put a bracket in this R cross F
So basically,
and
if
then
you
taken a dot product and
yeah.
then
So
uh,
here in the above equation, what you are doing, you are actually taking the projection of f vector also. So you have E dot r, which means you have some new vector r e, and you have E dot f, and you will have new vector fe. So this fe and re should be organizing in such a way that it will giving the movement. It will give this movement. So this fe is actually this vector f vector projected along e, and re is a r vector projected along uh, this direction.
okay. Yeah, I understood. Can you? Yeah, and I have one additional doubt also. So can you
Yeah.
please open that fourth lecture, please, one time?
Okay, let me first finish few problems of trusses. Then in the add on the At the end of the class, we can discuss about more problems. Is it fine?
Uh, yeah. Uh, it will take only 2 minutes because I need to go somewhere.
Okay.
If it is possible. Otherwise, yeah, please.
Okay.
Yeah, 10 minutes, 17 seconds. It is no week one, fourth lecture. Yeah, hai. Yeah, this here E dot R is written like bracket is not there. R in R cross F. So what I get is like we are just taking direction of R. Hello.
Yeah, yeah.
Yeah, in that. Can you stop there a little in previous slide? Just previous slide. Yeah, yeah.
Hmm.
Okay, here. So like here, we are taking projection of here. It is like what you have explained is one way. That is okay. I totally agree with that. And also you told that we can also take the like rotate the axis O towards O
Hmm.
dash, which you have
Yeah.
explained last week. That is also that I also like that is also correct. Like I agree with that. But here what professor is saying, like we take the projection of R in E direction, so we get a like a position vector along O dash, and then we taking cross product with R. So mathematically also it is wrong that we are taking a scalar and multiplying with the
Hmm.
vector.
Yes.
And yes, and mathematically is one problem, and one problem is like how this actually this projection will be when we take the projection of R in the direction of E. So that's why this is the problem. Your explanation I understood. Like
No, but you can always use this if you want to solve. You can always use this projection method to define the movement in the other axis.
yeah, that is okay, but is that mean that that is wrong?
Yeah, there might be issue in that equation because it's either there's a missing vector e component. It could be like this as well. R e dot r e. It could be this quantity as well, or
Yeah, yeah, yeah.
definitely
This, yeah, yeah. This.
there should be some missing stuff in that lecture.
Okay,
So anyway, you can
okay, and
advise.
just
Yeah,
yeah,
you can use equation
yeah.
one if you
What?
want. You can use equation one if you want to project the vector in some other another axis. That's what I'm saying.
Okay, yeah, and just okay,
Yeah.
and in the same lecture, just at 17 minutes. This is the last doubt I had.
Okay.
17 minute of 5 seconds in the same lecture. Actually, it is difficult to accept that there is some error, so that's why I just troubled you so much. Sorry
No,
for
it's
that.
fine. It's fine. I mean, sometimes it happens, but it's fine. I don't know if it is.
17 minutes and some second. Yeah, yeah, yeah. Yes,
Yeah.
a little. Okay. Uh,
So this problem actually we discussed in the tutorial. So we discussed this problem by multiple ways. Like we can take the perpendicular distance from the given.
Yeah, but my doubt is different.
Okay.
Yeah, that question, that I understand. Just 17 minutes. Can you stop at 17 minutes? Yeah, here. No, no, not here. 17 minutes. Exact 17. Yeah, yeah. Okay, but just stop here, please.
Hmm.
Okay. Here, one thing is like while taking a movement, can we take this x, y axis anywhere, or is it necessary to take at the point of application of force?
Oh,
One
it's
thing
it. No, yeah, you should always
like
take at the point of application only.
okay,
No, but the thing
so
is,
always take at the point of application.
but another thing is there is a
Yeah.
concept called line of transmissibility. So this we have discussed in the first lecture, and actually we use
Mhm.
the different concept to solve that problem. For example, I don't
No,
know.
my doubt is only there are two, three doubt. One thing is like, can we take origin anywhere while calculating a movement?
It's a point of application.
Only at point of application.
Yeah,
But because he also said that we can take projects anywhere. Okay, even if we take there only, then the equation is also can also be solved mathematically, right?
yeah, yeah,
Like we don't care about direction,
yeah. I
and we
mean,
just go maths by maths.
yeah,
So there can you just stop there? 17 minutes. Yeah. Now can you please, this m is equals to this equation,
yeah.
m is equals to minus this.
Hmm.
Yeah. Can you please elaborate it mathematically? Like if we take the first one, let's say x is x component of force, then it is in positive x direction, so it is positive.
Hmm.
Then the distance is minus 1.2. That's why this is coming minus this minus. But when we go for fy,
Hmm.
it is fy is also in the minus direction, and 3, this distance 3 is also in minus direction. Then mathematically, intuitively, we can say that direction is like this. But if we go mathematically only by Varigan's theorem, then this the second quantity will come out to be positive, because f direction of the f component, fy is in negative direction, and this 3 distance is also negative. So
No,
I'm just trying to solve it only mathematically. No, yeah,
no, but this is what we actually discuss and when we are trying to solve the movement question. Even in the previous question, I mean, we are now solving force and movement questions only, and we always actually define the direction of movement based on its rotation. For example, okay, let me give that example only, which is there in the video. So in the video, you have something like this. You have this force and this force, right? So this is your Fy and this is your
yeah.
Fx. So and you need to calculate the movement
And the
about point A.
origin,
This is our origin, right?
yeah, but please make the origin. No, A is not origin. The point of application of force is origin.
Okay, this is our origin.
Even if you take at A, you can also take at A. Only the directions will change. But what I want to calculate is how maths will project this movement direction.
Yeah, yeah.
That is
So
not coming in when I'm trying.
no, but we, yeah, this is what
Yeah,
I'm
you can
saying,
please.
because this to how to calculate the direction of movement, because this we actually do in every question. So even in the previous question we have done that. So it's not about taking the direction and the force direction separately and then combining. So for example, let's say if you want to take the movement about this point A, F, and and you are considering force Fx, you just imagine the rotation of this force about A. So imagine this force which is going in the positive x direction. Imagine that it is rotating about point A like this.
Yeah,
It is,
yeah,
oh,
but my question is that imagination I can do, but what I am saying that maths should also depict the same thing. that the direction should come in that direction. So
So
that's why I'm totally going mathematically and not taking any imagination, and I
so
just take the origin. Origin maybe can be at any point. If it can be at a point, can be at the point of application or anywhere.
but
From
this
there,
is
I should get the same result, but
but
I'm not getting.
No, but this is how we are creating the
Yeah.
mathematical equation, right? Because we said that okay, we want to create, we want to solve the movement at point A, and now it should be from fx multiply by x. Let's say it's a perpendicular distance x here, and plus fy
Yeah.
multiply by y. Now this is our equation. So the direction we need to choose. For example, we need to define the direction so that we can use in the mathematical equation. So here we just cannot simply say okay fx in the positive x direction and its direction is also positive, then it's overall it's a positive, because you are solving the scalar. So this is the scalar equation. You are not solving the you are not multiplying two vector. This fx is a scalar, this fy is a scalar quantity, this f is a vector quantity. This and this are the scalar quantity. This x and this y. This is a scalar quantity. So you cannot say okay my x is positive here and my fx is also positive here, because this is a scalar quantities. So you need to imagine the direction. Once you get the direction, you can, based on those direction, you can write the movement equation. So this is you will get when you imagine the rotation about point A. When you imagine the rotation about point A, then you can write down the movement equation. You can decide whether it is negative or positive axis, because unlike you are dealing with force vector and position vector, you just cannot say anything about its direction. So this is fx. Fx and Fy are scalar quantity. We only want to know about its magnitude. We can say the Fx is its direction is toward positive axis. Then what should be the direction of Fx multiply x? So this is a scalar quantity. It only have a scalar. It only have a value. It only have a magnitude. To define the direction, we need to imagine the direction of rotation about A, because this is what fx multiply x is showing. See, you have a point, you have this point, and you have fx here. You can easily recognize the direction of this quantity, which is force fx. But in order to get the direction of this fx x, in order to get the direction of this quantity, you just cannot say okay this is fx which is positive, going in the positive x direction, and this is going in the negative direction. No, you need to consider the direction of this quantity. You
No, but
cannot.
X.
Yeah.
Yeah, yeah, yeah. Not only I'm not talking only about force. I also direction. Like if we assume X, the origin at particular point, from there we also measure X, in which direction it is. Like it is in positive direction, negative direction. What I'm trying to make the point is
No, no,
the
I
math
get your
should
point.
also give
Yeah,
the same result.
yeah.
Yeah,
This is what I'm saying.
like X is also,
Here the math is only saying the
yeah,
same
like
thing, because you have a direction. Let's say this is fx1 and this is fx2. Now you say that okay, I am considering here a positive x-axis and I am considering here a negative x-axis. You decide your own coordinate here. Okay, you decide. I can decide here minus x and positive x. You can decide here positive x and here minus x. So here first you are deciding the coordinate system. Once you decide the coordinate system, then math will tell about the equation here, which is fx1 minus fx2 equal to 0. So math will tell this should be your equation. But first you need to define the coordinate system here, that this is my positive x-axis and this is my negative x-axis. Similarly, for the
yeah,
movement case, we are actually assigning the direction. Okay,
that's what
this is
I'm.
my positive rotation and this is my negative rotation. I decide my direction here. Once I decide the direction here, now my mathematics is saying this should be my equation. This should be my equation. This is what my mathematics is
So there
saying.
is no significance of origin.
Yeah, there is no
So there
significant.
is
Yeah.
in the lecture, because it was I was assuming that because that at particular point origin is taken as x and y direction, not
Hmm.
only this origin is taking, so like from that we can calculate the direction also, like if it is in particular direction, like x is also in a particular direction, we can define it as minus x I cap or
Yeah,
something like
yeah.
this. From that we can
Yes, yes,
calculate
because
the distance, like
uh-huh, yeah, yeah. So let's say at B, at point B, the direction of force is this, and you want to calculate the moment at A. You can see the direction around this point is clockwise. So you can write down the mathematical equation and you can easily find the movement. But at point C, if you take the movement at point C, the direction of movement is in opposite direction. It's a counterclockwise direction. So it can change your mathematics will change here. If you take the point C, you will the mathematical equation will get changed, and you will find that both have different mathematical equation, and you can see the direction of movement changes when you consider point C.
so basically, please can you open that slide just a minute? That slide, where the professor is explaining that. 70. Yeah. So here, uh, this 17 minute.
Hmm.
Yes, here. Okay, so here this is of we have this is wrong with what I am saying, that x in particular direction and minus 1 by 2, because it is in origin, it is in backward direction of x, and y is in negative, means a
Yeah,
from
yeah,
origin is at minus 3 minus 2 minus 3 minus 2, and fx is positive and fy is negative. This is wrong thing.
yeah. This is the wrong thing because when you want to define the direction of movement, define you have to define the direction of quantity f multiply x, not f and x and y and f2 separately.
Okay, okay, thank you. Okay,
And
understood. I will not go in that direction.
yeah,
Yeah,
and for
yeah.
example, let's say in this problem he considered the point A from which he took the movement. You can actually consider any point. You can consider this. Okay, I cannot write here, but you can consider any other point also, and it will actually give you the same result. So this problem actually we solved in
Okay.
the class, and we actually transfer this force at this. We actually transfer it. Just a second. So we actually transfer this force in this line, A line, at the bottom, at the very bottom we actually transfer the force, and we and even then we actually calculate the moment and we found the same answers. So let's say uh, this is your problem. This is A. This is the force. What we did, we actually transfer this force to here, and we take the moment and component here, and then we take the moment of this force here about A, and we found the same answer. And you can actually transfer this force here also. This is our force component, and this is our force. And then you can take the moment of this force about point A. Again, you will get the same answer. Or you can actually take the moment here. So, since this is the only force, you should get the same answer. You can actually transfer this force along the line of transmissibility, and the choice of the point where you take the moment, it should be a random, but uh, it should be like the equation will become simplified to solve. Sometimes what happens that you have multiple forces, and if you choose one point, it will you will have two unknowns. then you can not use only moment equation to calculate uh, the unknown forces. So I mean it's up to you. The point is it's up to you where to choose the point.
Okay. Okay, yeah. Actually, I had taken it wrong. Like I want to take it mathematically. That this I always we always do this thing, like
Hmm.
simply
Yeah.
imagining the direction. But I am just trying to get it mathematically, but that is wrong notion. Okay,
Yeah, yeah,
okay, okay.
it's
Thank you.
fine. I mean, it's no problem. The only concept is the first you define your Cartesian coordinate system and its all directions, and then you left it to mathematics, and then mathematics will govern you. But you need to first decide your own direction and via Cartesian system or any coordinate system you are choosing. That is only up to you.
Okay.
Okay, so I mean, it's good because we discuss these things now, because in in next problem we will be choosing, I mean, we will be using the method of joints, but we will be choosing some little Cartesian coordinate geometry. We will actually choosing different direction of Cartesian geometry, and then we will solve the uh, force in the unknown members by using equilibrium force equation. So this is just to simplify the equation. So let's consider another example problem. So let's consider we have a truss. So this is 30, this is 15. And there is 400 Newton force acting here. This is 2 meter, this is 2 meter, this is 2 meter. Okay, so as usual we will check the determinacy of the truss, and we can see that the number of members are 5, the number of reactions are 3, and number of joints are 4. So it satisfies this equation because the LHS is equal to RHS. Now we can use the method of joint here. So same concept, but I will show you that this problem have little, it's a little more mathematically involved. So consider joint C first. It's A, B, this is C, and this is D. So this is C. There is a external force 400, and let me first define my Cartesian coordinate system. It's a usual Cartesian coordinate system which mostly people uses: x and y, minus x, minus y, and this is, let's say, my, so this is my force CB, which is 45 degree. So this is my 45. Okay, then we do the usual exercise. We define the upward force positive, and if I do the summation of force in the vertical direction and equate it to 0, then I will have force CB sine 45 minus 400 equal to 0. So force CB will be 566 Newton. Okay, so this is positive 566, which is the assumed direction is correct, and it is going towards the joint, which means it's compressive force. Then assume the direction, this direction to be positive in the x-axis, then my summation of force in the x-axis should be equal to 0, and this will be F. Okay, I should there is one more force, FCD. There is CD also there. FCD minus 4CB sorry, cos 45 equals 0. So FCD CB is 566 cos 45 equal to 0. So FCD is 400 Newton. So again this assumption is correct, which means it's a compressive force. So okay, so this is the unknown force at joint C. So now consider joint D. This is D, and we saw that CD is compressive. So at joint D, this force at CD is compressive, which means it's a direction, it's towards the joint. This is force CD, this is force BD, and this is force AD. It's 15, it's 30. Okay, now we need to define a coordinate system. So first let me correct it on this. This is force BD and this is force AD. This is 15 and this is 30. Okay, so now we need to define the coordinate system. So here we define the usual coordinate system. You can define here also. You can just define here x-axis and y-axis like this, and you can solve this problem. But it will be very much challenging. Mathematically, it will be very much challenging. So what you can do? So now I define this axis, which is along FBD, is x dash. This is minus x dash, and the perpendicular to this axis is this. This is y dash minus y dash. So I define the coordinate system x-axis along force FBD. Okay, so when I define in this way, then I can do the summation of force first in the y direction, y dash direction, equal to 0. So now I need to consider the component of force in this y dash direction. So it will be minus force AD. This is my AD. Okay, so you can actually tell the component. So this is a perpendicular. So you want force along this component. Okay, so it will be sine 15 minus 400. Again, you want this component force, component of this along this direction, along this direction, because this is in y direction, right? This is in FCD in y direction. So it will be 400. 400 is the force we got. And it should be in sine 30 equal to 0. So Once you decide the coordinate system, you can see it's usual taking the component from the trigonometry or the sides of the triangle. So this is our equation 1. Then you can do the force balance analysis in the other direction, x at x dash direction. So now you need to do the force balance in this direction. So you need to find this component of force of CD and AD. FBD is already in that direction. So this direction, which is Fx dash equal to 0. So FBD is already in that direction, so I can directly write FBD. Yeah, no problem. Plus FAD cos 15 minus 400 cos 30 equal to 0. So all the forces like FAD and FACD, I am actually considering this component along this x dash direction. You can see that, sorry, this is our force CD and you need to define in this direction this component of force FCD, which is 400 cos 30, and similarly with AD. So this is our equation 2. So here the unknown are AD, FAD and FBD. These two are unknown. So FAD you can get from equation 1. So from equation 1 you will get FAD sine 50 equals 200. So FAD equals 200 minus sine 15. So FAD will be minus 772 Newton. So here you got the minus 772 Newton, which means the direction of force is it should be the opposite direction. So this is the force direction. This should be the force direction. And then from equation 2, if you use the equation 2, then you will get FBD which should be equal to 1.09 kilonewton. Okay, so the direction of force AD, you can see it's towards the joint, so it is compressive. And force BD, here the direction of joint is away from the joint, and hence it's tensile in nature. So the point of this question is, it's a regular truss problem here, and we need to use the method of joints here. But we saw that if we can change the coordinate system from the regular one, this is our regular coordinate system that you have seen in many books, x and y axis. If you change the coordinate system to this one, x and y, what happens that you can simplify the mathematical analysis, and this type of you can actually use the change coordinate system when you have a truss, which, like, when you have a members like this member and this member, both are actually having some inclination from the horizontal as well as vertical. You can see these two are having some different angle from the horizontal, like 15 degree from BD member, and this have a 30 degree from this horizontal member. This is 30 degree and this is 15 degree from this member. So in this type of problems, you can actually change the coordinate. You can define the coordinate like this. It's like inclined coordinate, and then you can actually take the component of force, like component of force of this member and this member along this coordinate axis, and you can do this regular mathematical exercise then. So by just just by using the different coordinate system, you can see you can simplify the mathematical analysis so much. Otherwise, if you use this coordinate system, you can use that, but the mathematical complication will be there. It will be little bit difficult, or the algebra will be more involving. So you can use this trick to find the force when you are using the method of joints. So the similar problem is here. So here you have a similar problem, like when you are using the method of joints to calculate the forces in the members, you can actually use the coordinate system like this here in this joint. But for the B joint, you can actually use the coordinate system along this direction. So one coordinate should be along this force, this member, along this member, or the along the force on this member, and one coordinate should be like this, perpendicular to this. So let's say this is y dash, so this should be x dash, right? Then you need to find the component of this force, these force, these force along y dash and x dash direction. And here you can simplify your analysis, mathematical analysis, uh, and you can actually find out very easily the unknown forces. So you can try to find the forces here at each member using the method of joint. So try this yourself. I will upload this PDF, and you can try finding forces. You can take any coordinate system. You can even take the regular one, like this is our x and this is our y, and try solving how you go solving in this coordinate system, and then you can try to solve in this coordinate system as well, and you can see yourself that how easily you can solve the problem. So this is very similar to the previous one that I have shown here. So try to solve the forces in these members at least. You don't need to find for each member here, just but consider solving force in this four members. Okay, so try this question by yourself. So any doubt you can ask. So in this question, now we need to figure out the zero force members. So there can be a zero force member in the truss. So these are the members where the forces are zero, but these members are still required to determine the stability. For example, let's say for example this is my zero force member. So the force in this member is zero, but this member is still required to make the whole truss stable. So the zero force member are essential members to maintain the stability. It is just that they don't bear any forces. So in this test we need to find out the zero force member. So whenever you need to find the zero force member, you should always look this kind of joint first, where you have a perpendicular kind of a joint, because usually in this kind of joint this member is a zero force member. So in this truss you can easily see that at joint G you have, this is our G, and let's say this is HG, and this is GF, and this is CG. So you can see that by inspection the force in this member CG, the force in this member CG is zero, and that you can actually find by using method of joint. So if you do the force balance analysis in the y direction, where you equate all the forces in the y direction to zero, you can see that CG is zero, because there is only one force in the y direction, which is CG, and that's all. And this is equal to zero according to the equilibrium force equation. And if you do the force balance analysis, you can actually define the relation of these forces, like Hg minus Gf equal to 0 and Hg equal to Gf. Similarly, you can consider joint D. It's a similar kind of a joint as G, because it has a perpendicular member. So if you consider joint D, this one, this is our D, this is our CD, this is our DE, and this is our DF. This is our DF, right? So now you consider the coordinate system like this, which we have discussed in the previous question. Let's say this is y dash and x dash. So if you do the force balance analysis in y dash direction and equate it to 0, you find that there is only one force in the y dash direction, which is dF, and that is equal to 0. And then the other equation will be is along the x dash direction, which is CD minus D equal to 0. So CD equal to DE. So from this summation of forces in the y dash, you can see that the DF force in the member DF is equal to 0, right? And now you can also inspect that if you define the direction, usual Cartesian direction, first you need to find the angle from the horizontal or vertical, and then once you get the angle, then only you can find the component of this force and this force, which will give you the same thing, zero forces. But you can see how mathematical involved it become. First you need to find the angle, then component of this force along x and y axis, then it will show you that the force in the df is 0. But if you choose the Cartesian coordinate here in x dash and y dash plane like this, you can directly uh, define the force df equal to 0, because this is the only force in the y dash direction, and according to the equilibrium principle it should be 0. That's all. So this is how, if you change the coordinate system according to your convenient, this is how you can simplify the mathematical algebra. Then you can consider joint F, this joint. Joint F. So this is F, this is D, this is CF, this is FE, and this is GF. So this is zero member force, so we don't need to consider this one, right? So let me take a regular Cartesian coordinate system here. This is y, this is x, and this is, let's say, some angle theta. And then if I do the summation of force in the y direction, then I can say that CF cos theta equal to 0, because this is the only force in the y direction. Okay, and the force in this member FD is 0. So another zero member force is this CF, which is 0. So this is also a zero member force. Okay, but this don't need to be a zero member force, because this is zero member force. Only then this is zero member force. Otherwise, let's say I have FD here and FC here. So this is my FD and this is my FC. So if I do the summation of force in the y direction, this is angle theta, this is angle theta, then I will get FC cos theta plus FD cos theta equal to 0. Okay, so if FD is non-zero, then force in the FC is also non-zero. But we saw that here, we saw that force in the FD is 0, which makes force in the FC also equal to 0. So if you have a perpendicular kind of joints like this, like in joint D and joint C, by inspection you can see that in the perpendicular joint the force will be 0, but then try to consider nearby joint as well and do the method of joint principle to see if it is 0 or not. You can say that, you can also see that this is also a perpendicular joint, joint B. So let's consider joint B. This is joint B. This is force 2 kilonewton. This is BH, this is AB, and this is BC. And if you do the force balance analysis, so this is my coordinate system x and y. So if I do the force balance analysis in the y direction, if I equate the forces and if I do the summation of force and equate it to 0, I can see that the force in the y direction are BH plus 2 equal to 0. So BH equal to minus 2. So as we discussed, for the perpendicular kind of a joint, the force in the perpendicular member is always 0, but here it is not 0 because there is a external forces which is acting. So this concept is only true when there is no external force, like here. So this is my perpendicular joint, but the force in the member is 0. This is my perpendicular joint, but the force here in this member is 0. But here in this member it is not 0 because of this external forces which is acting in that direction at point B. So if you have external force which is acting, then even at a perpendicular joint you may not find the 0 force member. And then you can actually uh, take other joints and check whether uh, you find the 0 force member or not by using the method of joining. Okay, so any doubt? So if not, then we can actually discuss the method of section in the next class. So in the next class I will move to the next topic, and before that I will solve two or three at least two problem of method of joint, and then we will move to the next problem. So that's it for today. Thanks. And I will upload the previous week and this week PDF, this PDF as well.